All right, back to it. Check, 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 check. All right, feels quiet. How about that? Just a little better. All right, we are going to start right at 11 a.m. Let me see if I can pull up the Zoom stuff today. Alright, share screen. I'm gonna pray that this works. It doesn't freeze. Try to sort out the technical difficulties right now. Alright. All right. How's this looking? So it's solid. Can we see everything? We got that. Okay. We got this. Cool. All right. I'm hoping it's working. I'm just gonna trust in this here. So we're gonna wait to start until 11. Might run out. Use the bathroom. Maybe change shirts. We'll see. All right, I'll be right back. Boom, boom, boom. 0 viewers? No way. Alright. It's nice talking to myself. I don't really mind it. Bum, bum, bum. Alright. Alright, what are we doing? Got this starting at 11. Put this up here. Yeah, we'll just wait to start here. See if we can play any music. What am I doing? Play some nice stuff in the background. Let's do oh yeah. Alright. Balls. Alright. Nice. So it is just about 11 o'clock in the morning on this Sunday with 0 viewers, but I'm making this in the hopes that someone's just going to watch it later on YouTube, so that's all right. Let's get started. So basically I have 18 problems picked out just to imitate what the exam will look like. It's just a bunch of random problems. Good variety. I couldn't choose all the ones I wanted to. There's tons of different problems, so I just picked the best ones I could. Before we jump into those problems, I'm just going to try to do like a crash course and a lot of the big ideas as fast as I can, so let's jump into that. So in quizzes 4 and 5, they introduced the idea of a derivative. So whenever you see the word derivative, don't be intimidated, don't be confused. Just think about it as the slope of a function at one point. So the slope at one point is a derivative. You might also see it called an instantaneous rate of change. Rate of change corresponding to slope, and instantaneous meaning at one point. So anything like rate of change, slope, derivative, the derivative of something like f of x is f prime. So if you see f prime, that also means derivative. Anything along these lines, like all of these are synonymous, okay? They also introduced at some point tangent lines versus like secant lines. So if you see tangent lines, there's kind of a connection between tangent lines of functions and the derivative. So like a derivative is very similar to a tangent line. More specifically, the derivative will typically equal the slope of a tangent line to a function, because the derivative is a slope at one point and the tangent line is a line that intersects a function at one point. And so there's a lot of like synonyms and different questions that will ask the same thing in different ways, right? So I just want you to like be aware of this and be able to look out for it, because like there's, I mean, like probably like 50% of the problems, I think it's on quiz, might be quiz 4, that will ask you to find like a slope or a derivative or instantaneous rate of change, or to estimate all of the above at one point, and it'll always pretty much use the same process. And we'll talk about that in a couple problems. Yeah, let's go over some random derivatives. So let's say we have a function, say 3x cubed minus 9x squared plus x plus 5. We are going to quickly demonstrate just taking a derivative using power rule. And again, once I go through a couple of these, just intro crash course ideas, then we'll start with our 18 questions. So taking the derivative, we bring out the 3 times the 3, we get 9x, and then we subtract the exponent by 1 to get 2. So 9x squared minus, and then we bring the 2 out, we multiply it by 9, so we get negative 18x, and then we subtract 1 from the exponent to get 1. The derivative of just 1x is just 1, because anytime you have a function that is just a constant times x, the derivative will just be that constant that was out in front. So same thing goes, had this been like 4x, the derivative would just be plus 4. And then anytime we have a constant, the derivative is just 0. So usually we're done after that previous term. So that's power rule. What other derivatives do you need to know? You need to know e to the x, the derivative of the function e to the x is e to the x. I'm going to do a few in a row here. So the derivative of e to the x is e to the x. The derivative of natural log of x is 1 over x. The derivative of, say, something like 4 raised to the x, or any exponential function that does not have e as the base, will be that same function times the natural log of whatever the base number is. So in this case, ln of 4. So we're just going through a few random derivatives here. What else do they ask for? I think you need to know sine of x. The derivative of sine of x is just cosine of x. And the derivative of cosine of x is negative sine of x. So sorry if I went through those a little too fast, but the deed is done. If need be, you can always scroll back later. But I'm just trying to do a few of these first. I think the last thing I want to talk about is like if you have to find a derivative of functions, say like this, wherever an x is in a denominator, what you want to do before you take a derivative is rewrite it. So if we were to rewrite this, we would rewrite it as x to the negative 2. We always want to rewrite something like this in the form of x to the a, so that you can then take the derivative of it using the power rule. So now that we have it in this form, we can take its derivative by bringing out the negative 2. So negative 2 comes out in front. We leave the x, and then we still subtract this exponent by 1. So negative 2 minus 1, that takes us further into the negative, so we get negative 3. So negative 2x to the negative 3 as our derivative of 1 over x squared. And if we wanted to, we could rewrite this so that the negative 2 stays on top, and then we throw that x to the third on the bottom, now with a positive exponent, because if it was x to the negative 3 on top, it becomes x to the positive 3 on the bottom. So then one more derivative like that I'll talk about is maybe square root, maybe cube root. I'll just say cube root of x. Same idea. If we see a function like this with any sort of root, we want to rewrite it so that it's in the form x to the a. And when we have the cube root of x, that is equivalent to x to the 1/3, or 1/3. So now that it's in the form of x to the a, we can take its derivative by pulling out the 1/3, leaving the x, and subtracting the 1/3 by 1. If we do that, 1/3 minus 1, my trick is to take the top number, so 1, so looking here, the top number 1 minus the bottom number, and then divide by the bottom number. So top number minus bottom number over bottom number. So 1 minus 3 is -2, and then we leave that over 3. So that successfully subtracts 1 from 1/3, or any fraction that we have. So then we get 1/3 x to the -2/3, and again we can rewrite that with x to the +2/3 if that term is brought to the denominator. All right, I think that's about all I wanted to cover real briefly. All right, let's start with our 18 problems. I have them pulled aside here, and hopefully this document does not poof away, because I've been having some problems lately where things just disappear. So, starting with number 1 of our 18 problems to mimic what the exam 2 might look like. Number 1, in this problem, they tell us that V is the volume, and V is also equal to F. So basically the volume is like our Y value, okay, or a function value. And then T is the number of years since 1960, and then they give us this equation. So like right when I get this problem, all I look at really is this here. First thing I start with is the T value. The T value comes from inside the parentheses, because f of t corresponds to f prime of, whatever's in parentheses is the t value. So t is 14, but then t is the number of years since 1960. So we just add 1960 plus 14, and we get 1974. And so we want to find an answer that at least mentions 1974 in the, in the statement. So we can eliminate the ones that don't even mention 1974. And then the other thing to consider in this equation is that they're telling us f prime is equal to -3,773. F prime means the derivative. Derivative means the rate of change of something. So the rate of change of f. In other words, rate of change of volume. So basically, anything along the lines of like recognizing the rate of change is equal to -3,773 will help you find the answer, right? So they're always talking about volume, change at the rate of this per year in 1974. That's basically what we're looking for. So in this case, B will be our answer. It'll never be one like C, not because of the years. A lot of people mention like it goes from one year to the next. That's not necessarily what makes it wrong. It's something about the wordiness of this here. I won't go too in depth, but basically we know that the rate of change is -3,000 something. That's telling us the volume will decrease by that much. But statement C is saying the rate of change of the volume decreases. Not the rate of change is -3,000. They're saying the rate of change is what's decreasing. So something about that makes it false. Anyway, B is right. Let's move on to number 2. I'm going to try to do these a little bit faster. If you need more of a breakdown, these are all the ones I've done videos on, so feel free to check those out. Mike, thank you. I appreciate your kind words. I need those a lot right now. You're very, very kind. It's always appreciated. All right. Thanks for stopping in. All right, so number 2. Let's see. They say H gives the height in inches and P is pounds. And so when we scan down to the last question, they say, which of the following expresses the instantaneous rate of change, or the derivative of the grass's height when 22 pounds of fertilizer are used? Okay, so right off the bat, recognizing first H of P represents the height corresponding to a given amount of pounds, And they're asking for the derivative, or the instantaneous rate of change, of the height when 22 pounds are used. Therefore, height is just h, but the rate of change of height is h prime, the derivative of height. And then if a p-value is meant to go in here and they tell us 22 pounds are used, then this will automatically be the start of the equation that they're looking for. So we can eliminate all the ones that don't start in this same way. And right away, that only leaves option E. So then we know that E will be our answer just based on that. And then we can also just find the rate of change that they give us in the statement. So they say 22 pounds of fertilizer, the grass is this tall, so that's just the regular height. But then they say it'll increase by 0.04 inches for each additional pound. So that's the rate of change. It's an increase in height per pound, right? So that's it. I hope that makes sense. Hopefully those are easy enough. Let's move on to number 3. Examining this sequence of numbers here and identifying if there's any sort of limit that applies to this pattern. So our options are all talking about the x values approaching 10. So the way we look at this is as we scan through these values from left to right, we want to ask ourselves, are these x values approaching any one x value? And in this case, they're going from 11 to 9.9 to 10.01 to 9.09. And as you can see, they're kind of like bouncing back and forth, but also getting closer and closer and closer to 10. And so the limit is definitely approaching 10. And then let's talk about the differences between these two briefly. When you see number 1 with approaching 10 with the plus sign, that means from the right. So from right. And then when you see 10 with a minus sign or a negative, that means from the left. And so if the sequence starts at 11, 11 is greater than 10. It is to the right of 10. But then it bounces all the way to 9.9. That is to the left of 10. And then 10.01 is to the right. So it's going right, left, right, to the left, to the right, or from the right, and then to the left, and so on. So it's bouncing back and forth, right and left, right, left, right, left, and then like honing in on 10 as it does that. And so in this situation, they're not going to consider that as from the right and from the left. They're just going to say it's neither like strictly from the right, nor is it strictly from the left. It is just approaching 10. So just 3 in this case. Hope that makes some sense. Let's go on to number 4. All right, so another limit one. This is more of like an algebraic situation. Whenever you see a limit problem, the first thing to try, in a problem like this, is to plug in the x value that they give you, okay? Generally, that's what you would do in this case. But they also mentioned like need help factoring. So the idea really, the route we're going to take is factoring. But let's demonstrate what happens if we were to plug in 3. So if we plugged in 3 to x up top, we'd get 3 squared, or 9 minus 9. And then on the bottom, we'd get 3 squared, which is 9 minus 5 times 3, or 15, and then plus 6. And so what's going to happen naturally is we get 0 over 0. And so the idea is if you get any sort of 0 over 0 case, what you should be able to do is rewrite the limit, or just like modify it in some way. And so in this case, factoring is the way to go. We're going to factor the numerator and we're going to factor the denominator. So the numerator, something to mention, x squared minus 9, that is a difference of 2 squares. And so we can break that up into x minus 3, x plus 3. And then the denominator is typical factoring. We need to find two numbers that multiply to 6 but then add to negative 5. And so multiplying to a positive 6 but adding to negative 5, that must mean both of these are negative. So x minus something, x minus something. And naturally, because we got this 0 over 0 case, what that means is like a factor on top must match a factor on the bottom. So if we know that like one of these on the bottom should match one of these on top, then that like forces, that's kind of like a hint as to like what one of these factors will definitely be, and that is x minus 3 in this case. So x minus 3 we have -3 times -2 would give us the +6, and then -3 plus -2 is -5. And so these are factors. And once we factor it and write it like this, we can cancel x minus 3's, and that leaves us with just x plus 3 over x minus 2. So now what we do is then evaluate the limit by plugging in the 3 wherever we see x. So if we plug in 3 on top and bottom, we get 3 plus 3, which is 6, and then 3 minus 2 on the bottom, which is 1. So we're left with 6. And that's it. Hope that makes sense. I'm trying to think if you could shortcut this or not. Yes and nah, I don't think so. I think it's worth just like figuring out how to factor. So for this one, factor, cancel out the factor that matches, and then plug in the x value. All right, number 5. Oh, good. Okay, I did another limit one. In this case, they're having us, I guess, plug in infinity, for lack of a better word, in any sort of limits that have like z or x going to infinity. What you're dealing with are basically horizontal asymptotes. And so you might have learned once upon a time about like how to identify whether a function like this, like a rational function, a quotient type function, has horizontal asymptotes or not. What we're going to look at are really just the higher exponent terms. So the leading term in the numerator, the term with the highest exponent, is -6z squared. And then if we do the same on the bottom, the leading term is just z squared. So when you're dealing with limits as z or x going to infinity, it's really the highest exponent terms that decide the overall behavior of the function, especially the end behavior. In other words, the behavior of the function as z goes to infinity. And so we can kind of neglect or ignore the other terms, and we're mainly focused on the higher exponent terms. So in the case that we have z squareds and z squareds, in the case that we have exponents on top and bottom that match, then what we'll do is just take their coefficients, -6 over 1, or just -6, and that will actually become the horizontal asymptote. Sweet. Thank you, Joseph. I'm happy to help. Thanks for just tapping in, but yeah, feel free to, rewatch it whenever you get a chance. No sweat. And so once we find that like -6 is our asymptote, that's essentially the end behavior of this function, or the behavior of it as z goes to infinity. So -6 in this case. I'll talk about like the 2 other situations you could have. They won't pop up too often, if at all, with these problems. But if you happen to see, say, something like this, say the leading term in the numerator was -6z cubed, and then the denominator was still just z squared. Then if the exponent up top is higher, then what's going to happen is, like, if you're evaluating this as z goes to infinity, then the numerator is actually going to blow up to infinity at a much faster rate than the denominator is. So it's basically like the numerator is blowing up while the denominator is like, it can't even keep up. And so this will just shoot off to infinity if the exponent in the top is higher than that of the bottom. I think I said that right. I don't know. Let's do the opposite case. If we had still just -6z squared was our highest exponent term up top, but then we had a z cubed in the bottom, then what's going to happen is the bottom is going to blow up to infinity at a much faster rate. Therefore, if we basically have, like, the denominator growing up, or like growing to infinity at a much faster rate, it's going to send the overall value to 0. And so that's kind of the different cases here. So in the first case, matching exponents, you take their coefficients, and that becomes your limit, or becomes your horizontal asymptote. In the case where the exponent's higher on top, it blows up to infinity. In the case that the exponent's higher on the bottom, it goes to 0. All right, let's move on to number 6. I'm going to kind of block off this vent. Hopefully the air is not too noisy. So, number 6. We are given a graph of a black curve and then a green line passing through it. And they're asking which of the following describes the slope of the green line. So first thing to recognize is that the green line, we want to recognize whether it's a secant line or a tangent line. So tangent, or secant. So in this case, green is a secant line. Why is it a secant line? It's a secant line because it intersects the function at 2 points, as opposed to a tangent line, which would have intersected the function at 1 point. So let me do a little line like this, something like that. That's fine. So this little orange line I've drawn here would be something like a tangent line right at, say, x equals 20. So tangent intersects once and kind of skims the surface of a function, while a secant line intersects twice. And so we're looking for the slope of that green line. So slope of this green line would really just be the slope between these 2 points at 15 and at 25. And so we're looking for something that represents the slope between 2 points. Slope between 2 points, like y2 minus y1 over x2 minus x1, or if we think about it like this, it could be like an f2 minus f1, or to be more specific, f of x2 minus f of x1. Basically, I'm just drawing this out, but we're looking for something like option D, because our 2x values we know are 15 and 25. If we went ahead and found the difference between x2 and x1, or 25 minus 15, we would get 10, and then x2 and x1 are just plugged in here, so 25 and 15, and so that's our slope between 2 points. Had it been, let's say we did have a tangent line situation, we would be looking for something like A or C instead, because that representation, this like limit representation with the h, always represents the slope of a function at 1 point. Therefore, the slope of a tangent line, because a tangent line intersects at 1 point. Okay, and both these statements are a little wonky. No need to go into detail why, but essentially if we had seen, say, a tangent line at 15 here, oh gosh, so something along this line, we would be looking for something like option A. The thing that was off about option A was just they have this negative here, which it doesn't need to be there. It should just be f of 15. So f of 15 plus a minus f of 15 all over h. This would be the slope of this red line here, because it's a tangent line and it's tangent to that black curve at x equals 15. All right, here's a good look at that question. Let's move on to number 7. In this question, they ask us to find the simplified difference quotient and the derivative of the function at x equals a for this function. So something I didn't mention at the very start, which I wanted to, was the difference quotient. The difference quotient is definitely worth knowing. It is f of a plus h minus f of a all divided by h. You might recognize it from the last question. The difference quotient is exactly what's in here, just minus the limit. So f of a plus h minus f of a all divided by h. So we are finding the difference quotient of this function. And so I'm just going to go ahead and call this function f just to be consistent. So this is f of x equals negative 8x squared. So let's go ahead and find f of a. What we're going to do is find f of a, and then we'll find f of a plus h, and then we'll plug each of them in here, subtract them, divide by h to find the difference quotient. So f of a is equivalent to f of 2, because a, they tell us, is equal to 2. So what we're going to do is just plug in 2 into the function f, wherever we see x. So that's just negative 8 times 2 squared. or negative 8 times 4. And when we do that, we get negative 32. And again, that was our f of a. So eventually, we will plug in negative 32 right there. But for now, we want to find now f of a plus h. I'll use a different color, mix it up. We'll do f of a plus h. Again, a is just 2. And in some problems, they'll give you an h value to plug in, but in this one, they do not. So I figured it was a good in-between type of problem. So we're going to find f of 2 plus h. The way we'll do that is by plugging in 2 plus h wherever we see x in the function. So rather than negative 8 times x squared, we're plugging in x plus h in place of that x, right? So we have negative 8 times 2 plus h squared. So the tricky part about these problems sometimes is being able to expand this, because what we need to do is expand it and combine like terms if possible. So I'm going to hone in on this here. I'm going to zoom in, and I'm going to start by distributing the 2 plus, or I guess expanding the 2 plus h squared. So that's really 2 plus h times 2 plus h. We can leave the negative 8 out. 2 times 2 is 4, 2 times h, 2h, h times 2, another 2h, and h times h, h squared. So I'm going to simplify this and hopefully write it a little bit neater. Yeah, that's pretty much it. Let me just do that down here. So we have 4, we have 2h plus 2h, 4h, and then h squared. And the last step, just go ahead and distribute this negative 8. So we get negative 32, negative 32h, or minus 32h, and then minus 8h squared. So this, again, is our f of a plus h. So this is what we will plug in way up here. Negative 32 is what we'll plug in for f of a, and then we will subtract them and then divide by the h. So let's go ahead and do that down here. We'll do negative 32 minus 32h minus 8h squared minus negative 32, all divided by h. So again, this here is f of a plus h. This is f of a, and we are subtracting them and dividing by h. Now, every single time, as long as you've done this correctly, f of a should cancel with the same term from f of a plus h. So because we have minus a negative, that is really plus 32 canceling with this negative 32, or minus 32. So those cancel. And what we're left with is really just these terms here divided by h. So we have negative 32h minus 8h squared over h. And we can basically divide out an h from the two top terms. As long as every term up top has an h, we can cancel an h. Or if you prefer, we can see it as factoring out an h in the numerator. So if we factor out from negative 32h, we get negative 32. If we factor out from negative h squared, we get negative 8h. And that allows us to then cancel those h's, and we're left with negative 32 minus 8h. So that negative 32 minus 8h is right here, negative 32 minus 8h. So that is our simplified difference quotient. Now, when they say find the derivative, well, we talked a moment ago about how this stuff with the limit represents the slope at one point, or the derivative. So all we need to do with negative 32 minus 8h is introduce that limit that was missing previously as h goes to 0. So in other words, just plug in 0 for h. When we do that, we get negative 32 minus 8 times 0, or just negative 32. So basically the h term goes to 0. We're left with negative 32. So we have the simplification number 3 and limit b. So 3 and b is what we're looking for. Hope this makes some sense. Let's see if I can get a view of all of it at once. Nah, it's not happening. Maybe all of this. That's cool. All right. All right, let's check out number 8. All right. Kind of similar problem to what we talked about 2 problems ago, but let's jump right into it. They say, number 1, the slope of the orange line is the instantaneous rate of change of f at 1.75. So right when I see instantaneous rate of change, that means the slope at 1 point. And because it's talking about 1 point, I kind of connect this to a tangent line. So what I'm looking for is the orange line a tangent line to the function at x equals 1.75? In other words, when we zoom in at 1.75, is orange just skimming the surface at 1.75? And I was about to say yes, but I think it's a close call, because if you look closely here, the orange goes below that black curve. So it's intersecting here, but then it's going below, and then it's intersecting again here. Therefore, it's actually a secant line. That's pretty crazy, right? So we are looking for a tangent line, but in fact, it is false because it was a secant line. Number 2, slope of the blue line is the instantaneous rate of change of f between 0.75 and 2.25. Now, the statement says instantaneous rate of change. We just said that's the slope of the function at 1 point. They gave us 2 points. Automatically, this statement is false. Had they said average rate of change, that would be acceptable. Average rate of change is another phrase for the slope between 2 points. And so what we would have checked for is the blue line a secant line, a line that passes through 2 points, namely at 0.75 and 2.25. So when we look at the graph, blue does intersect at 0.75 and at 2.25. Wow, so it would have been true had it said average instead of instantaneous, but it didn't. So it's false. Number 3, slope of the blue line is this. So when we see this, I want you to think about it as the slope between 2 points. This is very much like the y2 minus y1 over x2 minus x1 thing we saw a moment ago, or a different problem. But all we're looking for is a secant line through the x values 2.25 and 0.75, and that is the case here. So that's pretty much it. That is a true statement. So just number 3 is correct here. Leave that up for a sec. Michelle said, are the concepts you are currently going over going to be on exam 2? Or will there also be concepts you're not going over and be on the exam? Yes. So yes and yes. It's tricky because there are a lot of different things on exam 2. In other words, from quiz 4 and quiz 5. What I've picked are just like 18 random problems that I thought were good. I thought were good variety. That could be possibly on the exam. Yes. So what I'm going over could possibly be on the exam, but I will say I can't cover everything. If you have any specific questions, like during the session, let me know. Or I have videos working out all the different types of problems. But my best suggestion is just go over all the practice problems from quiz 4 and quiz 5, and those will be the possible questions that will be on the exam. And there's only 18 questions on the exam, so right now I'm just working through 18 random sort of questions. All right, so number 9, they say differentiate the function, this, and evaluate at x equals 2 and x equals -1. So to differentiate the function, that's just a fancy word that means go ahead and find the derivative of that function. And then to evaluate at certain x values means once we find f prime, or find the derivative, we're going to plug in the different x values that they give us. So let's start with the derivative. At the very beginning, we talked about power rule. It's important to know how to take a derivative or find a derivative using the power rule. So let's demonstrate that. Starting with 9x squared, we're going to bring the 2 out, bring the exponent out, and multiply it by whatever coefficient is there. So 2 times 9 is 18. We leave the x, and then we subtract the original exponent by 1, so we get just 18x to the first. We move on to minus 4x. The derivative of a constant times x is just that constant. so just minus 4. And then the derivative of any constant, minus 8, is just 0. So it really just goes away. And we're left with 18x minus 4. So now all we do is evaluate it at 2. So we're going to plug in 2 wherever we see x. So 18 times 2 is 36, minus 4 is 32. So f prime of 2 should be 32. We see that in b and c. We can eliminate the others. And then we evaluate f prime at negative 1. So again, we're plugging in negative 1 to our derivative that we found. So we have 18 times negative 1 minus 4. 18 times negative 1 is negative 18, minus 4 is negative 22. So that gives us option B, and that's it. Hope that makes sense. I'll go ahead and leave that there for a sec. And we're moving on to number 10. Take a little sip, take a little break. All right. Doing pretty solid on time so far. All right, so let's take a look at this problem. They say the following is a graph of f prime, the first derivative of f. Which of the following, based on this graph, which of the 4 graphs shown below could be a graph of f? F meaning the original function. So we are trying to find the function down here whose derivative graph is here, right? So what's the connection? We know that f prime is a derivative, and a derivative means slope of f, or slope of the function. And so wherever f prime, wherever this graph has positive values, I'm going to use a little color coding here. We're going to say wherever f prime has positive y values. You might have heard me say in the past where it's above the x-axis. Both of them mean the same thing. So wherever this graph is above the x-axis, or it has positive y values, for those same intervals, or like areas of the graph, like x value wise, let me reword this, from 0 until about 1.5, a little past 1.5 on the x-axis, f prime is above the x-axis. Therefore, on the graph f, we should have an increasing function for that same stretch of x values. What I mean is we should have a positive slope, because the slope of f is represented in the values of f prime. F prime, the y values, represents the slope of f. So what we're looking for in these windows, so from like 0 to 1. I'll say like 1.6, and then from about 5 through 7, 5 to 7 on the x-axis, we should see positive slopes of the graph that we're looking for, f. And so the only ones that even start, let's start with just this. So if we're just looking at from 0 to 1.6, this starts positive, this starts negative. It starts with a decreasing behavior, and so that can't be it. And then this starts positive, a positive slope, and then D starts with a negative slope. So D cannot be it either. And then when we look between A and C, A is a positive slope the entire time, right? So it's just going up the entire time. But C has a positive slope from 0 until about 1.6. So positive slope, there we go. And then from about 5 to 7, this curve is above the x-axis, or has positive y values, and so this one also has a positive slope from about 5 to 7. So positive slope, it's increasing from 5 to 7. Now let's talk about the middle of this graph here. So I'm going to go like overkill on this just to over explain it so you can apply it to other problems as well. When f prime has negative y values, then f should have a negative slope, or should have decreasing behavior. All right. F should have negative slope, or it should be decreasing. All right, so from about that 1.6 until about 5, this graph has a negative slope. And so negative slope corresponds to negative y values on the f prime graph. Hope that makes some sense. Anyway, C is our answer. There's a nice connection there for you. This is f and this is f prime. All right, let's move on to number 11. This is a fun one. Kind of similar. They say 3 graphs below represent f prime and f double prime. So the slopes of one of these graphs should be represented by the y values of another graph. What's like an easy way to go about this? Well, let's think about where the slope of certain graphs is equal to 0. So the slope of any of these functions is equal to 0 anywhere you have a maximum or a minimum. So like when we look at all these maximums up top, the slope of pink is 0 here. The slope of green is 0 here. The slope of blue, 0 there. And so let's like isolate what we're looking at. If we just look at the slope of pink being 0 at this max point here, if the derivative of pink is on this graph, then it should have a y value of 0 at that same x value. So along this vertical line, because pink has a 0 slope at that point, we're looking to see if any of these other functions has a y value of 0. In other words, crosses the x-axis at that same point. And so the derivative of pink is green, because when pink has a max, green is equal to 0, or it has an x-intercept. And so that means it'll be pink and then green if we are making a list. So like the derivative of pink is green. And so then if we did the same thing with green, we could say that, I don't know, green has a maximum here. But then the tricky thing is, if we, try to see what's crossing the x-axis, it looks like both of these colors are crossing the x-axis right below it. So that's a hard thing to judge there. Let's see if we can use another point where green has a minimum. Again, minimums work in the same way. Like wherever this slope is still 0, its derivative should still be crossing the x-axis at that same x value. And so where green has a minimum, its derivative must have an x-intercept. And so what we're getting at is the derivative of green will be blue. And this might have been luck. This might have been kind of using the intuition I know regarding a shortcut about this one. So hopefully we got enough like conceptual stuff. Let's talk about a shortcut. With this one, you'll notice that either above the x-axis or below the x-axis, you'll see kind of like a nice pattern with the maximums or the minimums of this function, depending on what problem you get. In this problem, we see this nice sort of like staircase of maximums, if that makes sense, right? Just going up and up and up and up. And it always is the case that like from shortest to tallest will always be the list of your f to f prime to f double prime. It's a brilliant pattern. Don't know why it works. I don't know why it is the way it is, but it works every time. I know the conceptual understanding behind it, but it's just convenient. The way they've set it up, it works every time. So from lowest to highest stair is f, f prime, f double prime. So our answer will be pink, green, and then blue. Something else to mention about this, sometimes you'll see the stairs kind of like upside down, if that makes sense. Like if there's a nice line of, let's say pink on the bottom here was more like this, and it formed this nice like stair situation with blue and green, then again from lowest stair to highest stair would be f, f prime, f double prime, if that makes any sense. So look out for that. That's a fun shortcut. Hope this makes some sense. I'm going to leave it at, I'm going to do the shortcut again for the correct reasons. So f prime, f double prime. I just wanted to make it so when you reference back at this, it made some sense. All right, let's move on to number 12. This is a good one. Always looks so chaotic with the answer choices here, but let's see if we can break down what we're looking at. They tell us we are studying the graph of population, and we determine that a tangent line at t equals negative 2.5 is given by this line here. So this line is the tangent line. Assuming that the tangent line provides a good approximation to the population of the species near negative 2.5, which of the following should hold? So we really don't know much about the population graph that they're talking about. All we really know is that there's a tangent line at negative 2.5, and we know what that tangent line is. Okay, so all we can gain from this is somewhere on a graph, or for some graph, for some function that represents the population, there's some graph with a tangent line at negative 2.5. So I'm just going to put a random dot in space, but on, negative 2.5. And we know this tangent line, the most important thing about this tangent line is its slope. So if we were to label this as y equals mx plus b, or mt plus b, or b plus mt, you get the idea. We're just looking for the slope, the number that's attached to the variable, in other words. So negative 2 is our slope. It's most important really just to know that the slope is negative. So of this line, so on this line we have a negative slope, and they tell us that this tangent line provides a good approximation to the population of the species near this point. All they're saying is, like, we can approximate the function's values. Like, let's say the function looks something like like this. So let's say this green curve is our function, and we have this blue tangent line here. They're saying if we if we went left and right, so if we went like here and here, these points would be, close enough to the actual value of the function. So we can use these points on the tangent line to approximate just like the relationship between these 3 points. I'm kind of going overkill on this again, but let's look at it for what it is. We have a tangent line at negative 2.5. It has a negative slope. The only thing that matters is whether that slope is negative or positive. So now we're looking at the values left and right of it. So left of negative 2.5, be very careful about this. Think about a number line and how 0 is, to the right over here. Negative 2.6 is to the left, and negative 2.4 is to the right. And because we're on a negative slope, all we're doing is like comparing these y values now. And so the y value represents the population. So where they're saying like population is greater than this population, you can just think of that as the y value. So the y value of the population at 2.6 is greater than the population at 2.5. And the population at 2.5 is greater than the population at 2.4. Sorry, these should be all negative. And that's basically the relationship that we're looking for. So now it just hurts my brain. I'm not a good reader here, but this is that's what we're looking for. So let's start with A and work our way through. So population at negative 2.4 is greater than the population at negative 2.5. That is not true. 2.4 is a much lower dot. So that's out of here. Population at 2.4 is greater. Nope, we just said that was false. Population 2.4 is less. Yes, so this point is less than this point. That is true. And then they say the population at 2.6, negative 2.6, population at negative 2.6 is greater than the population at negative 2.5. And that is exactly what we wrote here. So C is our answer. So went a little overkill in the explanation. All that matters is the t value, the points, making sure you have the correct like left and right points based on the ones they're asking about, and then the slope of the tangent line being positive or negative, because that sets the whole premise of like which points will be less or greater than the other points. All right. Number 13. Take a drink break. Take a stretch break. Alright. Let's get back into it. In this problem, they give us a table of t and f values, so like x and y values. And they're asking us about f prime at 0.9 and f prime at 0.4. So let's start with just f prime at 0.9. What we're going to do is focus on t equals 0.9. And we're going to look at the f values and how the f values are changing to the left and to the right of 0.9. So in other words, if 0.9 is here, we are looking at this f value to the left and this f value to the right. And as we scan through from here to here, from left to right, we ask ourselves, what are the f values doing? Are they increasing or are they decreasing? Increasing or decreasing? So from negative 9.5 to negative 12, that is a decrease. Earlier we mentioned when the original function is decreasing, that means that f prime, the slope, is negative. And that's all we need. So had it been an increase from left to right, then f prime would have been positive. So we can eliminate any that say f prime at 0.9 is positive. And that leaves us with just these negative options. So then we look at, I don't know why I deleted that. Let's get rid of, let's do this. All right. So now let's look at f prime at 0.4. So again, we direct our attention to 0.4, but again, we want to focus on the left and right points. We want to focus on how the function is changing from the left and to the right of 0.4. Because if we, analyze that, that'll tell us the information we need right at 0.4 approximately. So in this case, we take those left and right values, and really we're just actually finding the slope between those 2 points. The slope between 0.3 and 0.5 will serve as a great estimate for the slope or the derivative right at 0.4. So we're going to take y2 minus y1. So y2 is negative 7.6, and we're going to subtract negative 7.2. We're going to divide by 0.5 minus 0.3. Up top, we'll add the 2, so it'll be negative 7.6 plus 7.2, and that'll give us negative 0.4, I think. And we're dividing that by 0.2. And when we do that, dividing by 0.2 is the same as multiplying by 5. So 0.4 times 5 is 2, and it also had the negative. So we get negative 2 for f prime of 0.4, so we can eliminate b, and c is our answer. Hope that makes some sense. Finding the slope from the left finding the slope between points left and right of a middle point will serve as a great estimate for the derivative or instantaneous rate of change right at that middle point. All right. Here's a fun one. Here's one where they just like throw information at you and just assume, it makes sense what to do with it. Let's break it down. We are told that the instantaneous rate of change, let's go ahead and just think about that as not even derivative, but just slope. We are told that the slope for a given function at x equals 9.6 is negative 1.5. The slope is negative 1.5, or m equals negative 1.5. Further, we know that f of 12.6 equals negative 9.5. That's saying when the x value is 12.6, the y value is negative 9.5. Which of the following values for f of 6.6 is most consistent with this information? Now, what we need to do is just use this. It's strange, but we can ignore 9.6, I'm pretty sure. All we were gaining from that was like the slope of the function was negative 1.5. And so we're given this x value, we're given the y value, we have an m value. We want to find that value. Okay, so what we're going to do first is find basically a tangent line. We're going to find an equation for a tangent line. Once we have that, we will plug in 6.6 and get a y value and return. All right, so setting up an equation for the tangent line. If we think about it, an equation of a line, that's just y equals mx plus b. if we have m, if we have y, if we have x, we can plug all three in, and that'll allow us to solve for b. So let's go ahead and do that. Plugging in y, we get negative 9.5 equals m, negative 1.5, x, 12.6, plus b. Grab my phone. I'm too lazy to do Desmos. What we're going to do is, I'll go ahead and just add this combo over here. So add 1.5 times 12.6 equals b. So I'm just going to type all this in and calculate b. 9.5 negative plus 1.5 times 12.6. That gives us b equals 9.4. Again, that's not our answer, but that is our y-intercept. Why do we need that? We needed the y-intercept because now we know what our b is. That's 9.4, and we can plug in our m, negative 1.5, and now this is our slope, or sorry, this is our equation of the tangent line. With this equation of the tangent line, we've constructed a tangent line that will serve as a good approximation of the other function values, and so that's why we're trying to estimate f of 6.6 using this information. So what we'll do is just plug in, what was it, 6.6 negative? No, just positive. So we're plugging in 6.6 for x now. And we're calculating the y value. So let me do this. 1.5 with a negative times 6.6 plus 9.4, we get negative 0.5. And that, hopefully, should be our answer. And that's it. So really, not very clear problem here. But, again, when you look at it, they're giving us the slope, negative 1.5. They give us an ordered pair. That's huge. X and y values. We plug those into y equals mx plus b, and that allowed us to solve for b. And then we set up, mx plus b with the m and b actually plugged in, and then we plugged in the 6.6 that they gave us here. All right, let's get a good glimpse at that. All right, let's keep going. Number 15. This is actually the same exact process, except it's a little bit easier in my opinion. All right, pick the choice that's closest to the y-intercept. We are finding a b value of a tangent line, right, for this function at this x value. So let's think about what we needed in the last one to find that b. My pen break? Okay, there we go. We needed an x value. In this case, we are given an x value, negative 0.55. I'm going to do what we need first, and then I'll write them out. So in the last one, we needed an x value, a y value, and a slope value. The x value in this case is given to us. The x value is negative 0.55. The y value in this case is not given to us, but we can find a y value that corresponds to this x value by just plugging in negative 0.55 to the function sine of x. So we will find this value by plugging in 0.55 in place of sine of x, or in place of x and sine. So we'll find that. To find the slope, we need to find the derivative of sine. So the slope of a tangent line will always come from the derivative of whatever function you're dealing with. So g prime, and the derivative of sine is positive cosine. So we'd have cosine of x, and then to actually get a slope value, then we would plug in the x value we were given, and that is still negative 0.55. So we'd plug in negative 0.55 into our derivative, and what we find for that will be our slope. Once we have our x, y, and m, we will plug them into y equals mx plus b, and that will allow us to solve for b, which will be our y-intercept. So, using my phone, we're going to do negative 0.55, and then we're going to hit sine. That should give us negative 0.523. we have a y value, we have an x value. Now we need to plug in 0.55 with the negative 0.55 into cosine, and that will find us the slope. When we do that, we get 0.8525. All right, we have our m, our x, and our y. We're going to plug them into y equals mx plus b. Plug in the y, negative 0.523 equals m, 0.8525, x, negative 0.55, plus b. And we're going to solve for b, and then we'll be done. So I just went ahead and multiplied these two, and I got negative 0.469 plus b, still equal to negative 0.523. All right, and we're going to solve for b by adding this to the left side. So we get 0.523 with a negative plus 0.469, and we get negative 0.054, pretty close to 0. Let's see what they have here. Okay. Tough call here. They don't give us very many close options, do they? Negative 0.1 might be the closest. Yeah, that's pretty whack, I'll be honest. I mean, yeah, that's got to be the closest. I don't know why they didn't have any closer value, but anyway, the closest value to this is negative 0.1. I don't know if my rounding was weird. Maybe if I had used more decimals here, it would have gone a little better. But I guess that's just the way the cookie crumbles. All right. To find the y-intercept of a line that is tangent, or a tangent line, we need x, we need y, which we find by plugging the x value into the original function. We need m, the slope of the tangent line, which we find by plugging in x to the derivative of the original function. Once we have x, y, and m, we plug them in here to find b. All right. Number 16. Surface area, S, of a spherical cell is proportional to the square of its radius. So all that is just saying what this equation says as well. So really, just look at this equation. Which of the following is the best estimate for S prime when R equals 156? So all we need to do is find the derivative of S, and then we will plug in 156 wherever we see R. So let's talk about this. 4 pi is just some constant, but really it's a coefficient for the r squared term. So any coefficient for any variable, term sort of just gets carried down into the derivative. Or let's think about it like this. If we're taking the derivative of r squared, we bring out the 2 and multiply it by whatever number is out in front. So 2 times 4 pi is just 8 pi. And then if we're still dealing with the r, we leave the r and then we subtract the 2 by 1. So 2 minus 1 is just 1. So we have 8 pi times just r. So that is S prime. Now S prime at 156, we are plugging in 156 wherever we see r. So now we'll just calculate 8 pi times 156. And when I did that, I got 1,407.4. So we're just picking the closest. I don't know why they do that, but I guess it was meant to be like an estimate thing. Anyway, yeah, so we find the derivative doing that. We get about 1,400. That's close enough to one of these options, B or C. And we want to pick the one that makes the most sense given the units. So if we found the rate of change of S, but S represented the surface area. The units are in whatever the units are squared. So that's like micrometers, I think. Had it been talking about volume instead of surface area, it would have been micrometers cubed. So in this case, it's just micrometers squared. And then because our independent variable, the R, is also in terms of micrometers, it's like micrometers squared per micrometers. It's kind of whack, but That's our answer. All right, number 17. Nice quick one here. They tell us to find f prime at pi, or f prime of pi, when f of x is equal to x. So we want to find the derivative of this function and then plug in pi if we can. The derivative of 1x is 1. Because there are no x's to plug in a pi here, the derivative at any x value, including pi, is just 1. All right, number 18. Also a nice kind of quick one to end it on. In this problem, they give us the graph of f, and they ask for f prime. So the graph of f, what's the relationship? The slope of the graph of f is what tells us the y value. So slope over here is what tells us the y value of the derivative of f prime, because f prime represents the slope of this graph. The y values of f prime represent the slopes of f. All right, so what's the slope of f? Well, it's going, down 1 over 1, down 1 over 1, and so on. The slope is -1. So we are looking for the y value of -1 on this graph. And the only line that has that is orange. And that's it. And that marks the end of 18 problems. All right, I think I'm going to call it here. I'm going to go ahead and scroll through all these problems just so you can get one last glimpse at them. If this helped you, I'm happy to hear it. If you have any other questions, feel free to email me at carterdeemath@gmail.com. And if this helped you, please consider donating to my Venmo. I think the handle's in the description as well, Carter D. But I'll put it here as well. If this helped you, then I'm happy to hear it. And sorry, I lost my train of thought. Yeah, send a donation if you're feeling generous. If not, that's fine too. Happy to help regardless. Let's scroll to the top here. All right, again, I'm just scrolling through all these just so you can get one last quick glance at them. So you can have them all in one place, basically. Limits, covered a lot of good stuff today. Limits, covered horizontal asymptotes or limits as x goes to infinity. Covered tangent lines versus secant lines intersecting at 1 point versus 2 points. Covered the difference quotient and the limit definition of a derivative. More tangent lines versus secant lines. Tangent line correspond to anything that's a derivative at 1 point, so instantaneous rate of change, derivative, f prime, whatever, and then secant lines correspond to 2 points, and so that's average rate of change, slope between 2 points, all that jazz. You'll want to know how to find a derivative using power rule. You want to know the relationship between f and f prime. Good stuff there. Knowing the shortcut here could be helpful, but again, it really just uses the relationship between f and f prime, because the relationship between f and f prime is the same relationship as between f prime and f double prime, right? All right. In this case, they mentioned stuff about tangent lines. Hopefully that made sense when we talked about that. To estimate the derivative at 1 point, we always want to use points left and right of the desired point and find the slope between those 2 points. More tangent line stuff here. More tangent line stuff here. Derivative stuff again. In this case, when they said best estimate, to estimate the derivative at 1 point at 156, I think we could have also used finding the regular surface area at 157, and then the surface area at 155, and then divided that by the change in 157 minus 155. In other words, picked an r value to the left and right of 156 and then found the slope between those 2 points. So that probably would have gotten you something a little closer to negative 3900. Oh boy. Did my thing just cut off? What just happened? Oh, something just popped up. Okay, we're good. All right. Anyway, yeah, we could have done that for 16. I think it's still working, hopefully. Number 17, derivative of x or any variable is always 1. There are curveballs with these ones. I remember in the past where they'll say like f of t is equal to x. And in this case, t should be the independent variable. So if they say the function is x, that's just another way of saying like the function is constant. And so the derivative of any constant would just be 0. So had it said like f of t equals x, the derivative would be 0. But had it said f of t equals t, the derivative of the correct variable is 1. Hope that made some sense. Number 18, again, the slopes of f are represented in the y values of f prime. All right, I'm going to call it here. I'll be working through, y'all don't care, I'm working the 1026 review later, but that doesn't deal with y'all. So, all right, thanks for tapping in. I'm going to call it here. If you have any questions, please let me know. All right.